Gone.
Good morning, sir.
Yeah. Okay. Mokshi, can you hear me?
Yes, sir, I can.
Mokshi?
Yes, sir, I can hear you.
Fine. So, yeah. So this is where we stop, right? So this is where we stop that day. We derive the canon. We also talk about the how to solve them, the iterative procedure. Okay. So all we got is from there. Yeah. So all we got is the solution of canonical Hartree-Fock equation f of, let's say, 1. All this is not one, right? So you got a number of solutions. Not only this set chi, just like when you solve an atom, you have only one electron there, but you got orbitals, infinite number of orbitals. Derive this sum of electrons will give us one electronic part. Uh, it's gone. Mokshi, can you hear me? Still you are there?
Yes, sir. Just now you joined the class.
Yeah, it got in between. It got. Internet got disconnected.
And earlier also you were not clear to me.
What to do? This was a problem of this room. JBC doesn't know network problem. After last day. Yeah, so if you remember Mokshi, this is where we started, and after deriving the equation, we got this set of
So you
equations.
haven't shared the screen.
So if you solve this set of equation, you get a set of chi i's. From that, I have not shared my screen.
Yes, sir.
Got disconnected. Yes. Yeah. So once you get the set of chi i's, you put the with that set of chi I, you construct psi naught, and from that psi naught, you take the expectation value of electronic JI, right? Remember this is from then we also have written in some other way one to n this of this you can write when you compare Mokshi, are you recording this?
Sir, I think the host can record.
If I record, then it will take to record that. Shiva is recording. Shiva, are you recording this? Okay, then you share with them. Okay, fine. So that's type of atomic orbital basis. We'll come back to the point much more elaborately. These are antisymmetrized true electron integrals. Right? So that's all we got. Okay, so after variation, after solving that non equation, you have to get. So this energy is E Hartree-Fock. Within Born-Oppenheimer approximation, for every single nuclear configuration, we get this energy. If you want to optimize your molecular structure, then according to Born-Oppenheimer approximation, you change your nuclear position, get another Hartree-Fock energy, keep on doing that till this energy is minimum with respect to nuclear coordinates. See, this is minimum for a single nuclear coordinate, right? This is minimum with respect to chi-i's, electron orbitals. But this also, if you remember that our electronic Hamiltonian age, electronic was parametrically dependent on nuclear coordinate Ri. If you change nuclear coordinate, electronic Hamiltonian will change as a parameter, right? So for different electronic Hamiltonian, different nuclear position, you get different Hartree-Fock energies. If you join those plots, if you plot it, then you get a minimum. That minima is the optimized structure, right? Those are the next level. You can do those, but this is a single point Hartree-Fock calculations for a given nuclear geometry. If you solve this equation and put in this expression, you get Hartree-Fock energy for that particular point, right? Now, let us try to understand what else we still don't know what is physical meaning of chi, right? Let us see what does it mean. We have in this expression f of 1 chi I of x1, we gave epsilon I chi I of 1. If we take the expectation values of this with respect to chi I1 star x1, f1 chi I x1 dx1, you get right hand side epsilon I integration of chi I star x1 chi I x1 dx1. You see this guy right side is 1 because these guys are orthogonal. So this is equal to 1. So what we get? We get epsilon I equal to integration of chi I star x1 f of 1 chi I of x1. So this is what? This is the expectation values of Fock operator for a given one electronic orbital, one electronic function. So if that is the case, then this is related to the orbital energy, right? So chi I we get a set of chi I epsilon I get there are the orbital energy. Right? Now, if you add all the orbital energy, then what should you get? We are supposed to get the total energy. If I have n number of electrons, if I get n orbital energies, we are supposed to get total energy. At least that's what we can think. We may get total energy equal to sum of orbital energy. So what you do here, you sum over all I epsilon I, right? You do this, what we get? Sum over of I chi I star x1, right? f1 chi I x1 dx1. Put this sum, let us expand chi I star x1. What is f? Let us break f now. F is h1 plus sum over of j integration of chi j star x2 1 upon r1 2. I write in that old fashion p1 to pi j of x2 dx2, right? And then I had chi I of x1 dx1. Expand this, what we get? There is sum. There is sum, and then the first time we get integration of square star x1 h1 chi I of x1 dx1, and then this sum will be there. I have this sum, I have this sum, I have this integration, right? And this integration that already I have to carry. So I have two integration, one will be over dx1, one will be over dx2. So I get chi j star x2 1 by r1 2 1 minus p There is a chi x1 star, right? I missed that. There is chi I star x1, and then this chi j star x2, 1 upon r12, 1 minus p12, chi I of this chi was there, chi j of x2, chi I of x1, dx1 dx2. Right? You have to just write the next line. That's all about it. You see this guy, the first term on that summation, this one, if you write in Dirac notation, I can write sum over of I, chi I, h, chi I. Right? This term, can you tell me what is this term? This is Coulomb minus exchange. Right? This is basically, if you write in that notation, this is basically I, J, let me write, sorry, that other way. This is basically chi I x1, chi j of x2, 1 upon r12. This one will give me chi I of x1, chi j of x2. That is this one and the rest of the part, right? Then minus chi j x2, 1 upon r12, this chi sum of j. What is it out? Okay. I have chi h chi I plus sum over of I, sum over of j, chi I chi j, double symmetrize. This is the total orbital energy epsilon I. Right? And this will be the article and the equation have written today. What is that? Total Okay, Mokshi, are you here?
Yes,
This
sir.
part?
Yes,
Okay.
sir.
So let me write this again. We have to I I H I I plus sum over it was half sum over I sum over J I. Right? So this is the total orbital energy. This is the Hartree-Fock energy. Now, can you see the difference between these two? What is the difference? There is half. Now, question is why half is extra here? Any answer? This is sum of the total orbital energy. This is sum of the total Hartree-Fock energy. Right? Orbital energy. We should get the total energy, right? But we are not getting it. We are getting something more, right? Why so? Before asking this, answering this question, why so? Let us try to understand what this equation means. Okay, the Fock equation. That's more important. What is the meaning of this Fock equation? So let me write it again to be easier. What is Fock equation? This is the Fock equation. Psi I chi I of x1 equal to epsilon I chi I of x1. Let me expand this. This implies that I have h of 1 plus sum over of j integration of chi j star x2 1 upon r1 to 1 minus p1 to chi j of x2 operating on chi I of x1 give me a pseudo eigenvalue equation epsilon I chi I x1 back. Right? What does it mean? You see, normal eigenvalue equation, what is the way we write, let's say I'm writing A is an operator, operating on a wave function, give me the eigenvalue and eigenfunction back. Right? So one, many does not matter. It is this is the function, this is the operator which can operate on the function. So this will have only the coordinates, right? Property of the system. But what we got here, you try to understand that we started with many electron problem. In our hand, we did not have one electron, we have n electrons. For example, for water, we have 10 electrons. But the equation we got, if I, it looks like one electron. Right? So this is also known called as independent particle approximation. If you consider this equation, it has your operating only on electron which is located or situated on x1, which coordinate is x1, right? The Fock operator can operate only on that coordinate. So basically, as like I have electron on electron is equivalent on 3. We have all 10 electrons. Yeah. But when we are solving, we are solving for each electron separately, as if they don't depend on each other, because this equation is one electronic uh, equation. But is it really so? If I expand it, the next equation you see, the other electrons are there.
Excuse me, sir.
Here, J electron or J orbital are here. Particles. And calculate it one to n. Hello, Mokshi, can you hear me?
Sir, I lost the connection. I am not able to follow up
Okay,
the difference you were telling about the
yes. Let me.
electrons. Yes, sir.
So why did you lost the connection here? Did you follow
Sir, when you were
this one?
explaining, sir, you just wrote this equation and you were telling about the eigenfunctions and eigenvalues. That's it.
This.
Yes,
Yes.
sir.
When you write a normal eigenfunction, this operator does not depend on these functions. They are operator, they are function, they are separate entities, right? If you look at this equation, as it looks like an operator, a Fock operator, operating on a function, give me corresponding eigenvalue and the function back, as if it's an eigenvalue equation, right? Now, if you want to, let's say I have electron number 1, that is the coordinate will, its coordinate will be x1, right? That is occupying in the ith orbital, okay? So if I do that, then I can solve this equation for electron 1. Let's say I have solving this equation for another electron, let's say F2, operating, that is located on orbital chi j x2, I'll get similarly epsilon j chi j x2. So there are n number of equation. Each equation will give me a solution of the orbital. Each equation will give me a set of orbitals and the orbital energies, right? So as if when I solve this equation, we don't really talk about chi j. So this equation, at, at least on the outside, there is no other electrons. It's only focus of electron x1 located having coordinate x1. This will focus on electron having coordinate x2 occupying chi j orbitals, right? So if you just look this equation, this is just one electronic equation, like pseudo eigenvalue equation for every electron separately. When you solve for I, I, when thinking of if j equal to 1 to n, but in that whole set, I have excluded chi I. So there are n minus 1 orbitals are there, and I have integrated all over their coordinates and sum the effect, right? So this means that when we solve this equation, when we construct the Fock operator, all n minus 1 electronic effect has been summed up, integrated and summed up, right? This is called spherical averaging. So when you're looking for electron number 1 for say, rest 9 electrons will together form a potential. That potential will be included here. So every operator, when you're talking about electrons, have kinetic energy part and potential energy part. This HI has already its kinetic energy part. It also has potential energy part, that is the attraction between electrons and the nucleus. Electronic repulsion part, that is included here. That is also potential energy. And how are we including it? We are including by averaging n minus one electron repulsion. So when we are considering ith electron, that's the first electron, then all n minus or 9 electrons interactions, their repulsion, we are averaging them. How are we averaging them? By this. In continuous, like this, we're summing over effect of all. So that is there inside. So this equation, you solve for only one electron. Other n minus electron are effective take as average. So this is the reason it's called, this is spherically average out. Your net is your net is there. No, it's a probably room problem, something I don't know. I see there's some other issue. Yeah. Mokshi, can you hear me?
Yes, sir, now I can hear you. Yes, sir.
Mokshi,
Yes, sir.
are you there?
Yes, sir, I am.
No. So, uh, could you listen what I was talking about the spherical averaging?
Sir, Sir, I listened up to the point you were telling that the orbital energy is sum of only one electron. The other electrons are not counted. Hello?
Okay, so you understood what it means. Yeah, now again we got. Okay, so up to this point that I was talking about, that when you talk about orbital energy, when you solve this equation, you solve only for one electron, right? Mokshi?
Yes, sir?
Mokshi, is that fine?
Hello, sir. Am I audible to you?
This is the point that you follow, right? When you solve this equation, we solve only for one electron, right? My voice is. Did you follow up to?
Sir?
Yes, Mokshi.
That every time you start explaining, the voice is cutting down.
Yeah. So let us do one thing. Let us stop today. Thursday we'll get back to you. Okay. I don't know. I have to figure out what is going wrong here. Maybe this room or maybe I don't know. Okay. Let us figure out what's going on. Okay.
Okay,
And
so
yeah.
shall I leave or you are recording the class also?
Uh, yeah, we're recording the class. One of my students is recording. Okay, no
But
matter.
he might be facing the same issue.
No matter, we'll start again from here. Next
Okay.
class, we'll start from here.
Okay.
We are also not sure, sir, how far it is coming.